All right, welcome to an intro to GLIBC heap exploitation. My name's Max, and it is my quest to convince people that Linux heap exploitation isn't as difficult as it seems. If you haven't done so already, please exercise poor cyber hygiene by plugging USB sticks into your laptop. Does anybody need one of these? Stick your hand up. Just this gentleman over here. Can someone pass him a spare one? If not, good catch. Boot it up full screen. There should be a VM on there, sorry. Should work with either VirtualBox or VMware. Boot it up, full screen it, sort out the resolution, etc. They should log in automatically, but if they're not playing the game, username is heaplab, one word, all lowercase, and the password is also heaplab, one word, lowercase. So if they mess you around, just use that and you can SUD or all you like. Right, so once you guys sorted that stuff out, I'll give you a brief description of what we're doing here today. So for those of you unfamiliar with it, GLIBC, or GLIBC, stands for the GNU C library. It's a shared object, the Linux equivalent of a DLL, just like any other. It's also a fundamental part of any Linux operating systems, both desktop and embedded, including distros like Ubuntu, Debian, and Arch Linux, to name a few. And simply put, on your average Linux distro that doesn't use a libc alternative like Muscle, you have to find a process that doesn't map the glibc shared object into memory. And all glibc actually does is provide some boilerplate code, functions like memcopy and printf, to programs written in C and C++, and by extension, some of the higher level languages like Python, whose interpreters are. Now, glibc also provides a dynamic memory allocator, known as malloc. Dynamic memory allocator is used when a program can't know the size or number of objects it needs prior to runtime. And malloc's job is to dish out so-called chunks of that dynamic memory to processes at runtime. And those chunks come from large contiguous blocks of memory known as heaps. If you've ever dealt in C, chances are you've used malloc. A little more abstracted, the new and delete operators are thin wrappers around malloc, as are by extension make shared and make unique. Even if your code doesn't explicitly invoke malloc, chances are one of the library functions you're using does. Starting a new thread, opening a file, or dealing with I/O all use malloc under the hood. So, the fact that malloc is so widely used, combined with the fact that it's used in languages like C and C++, for which memory corruption is still an issue, both make it a great target for exploitation. And that's what we're doing here today. We're going to learn two heap exploitation techniques, the first called the House of Force, and the second known as a fast bin dupe. Our tools of the trade are the GNU debugger, GDB, enhanced with a Python library called pwnbag, and to help us interact with the vulnerable binaries will be exploited later, a second Python library called pwntools that I'm sure a lot of you are familiar with. So if everybody's comfortable with what we're doing, we'll dive straight in. And those of you who have just arrived, if you can grab a USB stick off of someone else, you should be able to import the VM. Did you need a USB stick? Oh, you got one. So malloc itself is just a collection of functions and metadata for the purpose of dishing out those chunks of heap memory to processes. And today we're concerned with two of malloc's functions, malloc itself for requesting heap memory and free for recycling it. Yes, it is a little bit confusing to have a function called malloc used to request heap memory from the dynamic memory allocator, also called malloc. But at least it's a simple function. It takes a single argument, the size in bytes of memory that you want, and it returns a pointer to that amount of memory, or slightly more, for you to do with as you wish. And to help us visualize how heap memory is requested via malloc, we're going to debug a small demo binary. So, switch fire to your VMs. Hopefully you've all got one running. And open a terminal and navigate to the House of Force directory, in which you'll see a couple of binaries and scripts. Should look... bear with me. Can you read that at the back? Is that all right? Awesome. So you should be able to see a couple of binaries and scripts in there. We're going to debug the demo binary under GDB with the command. Once you've done that, we're going to set a breakpoint on the main function with break main or just b main. And then we're going to run the binary with run or just r. Can you read what's in the bottom left there? Or is that still covered up by the lectern? All right, close enough. Welcome to Pwn Bag. So if you've used other GDB enhancement suites, you should be right at home. And there's a lot going on the screen, but all we're concerned with today is the source panel, that third from the bottom, in which we can see that all this program does is request heap memory with the malloc function a bunch of times. Starting with this request for 9 bytes, just an arbitrary number, and it will save the return value in a variable called a. So before we let it do that, we're going to introspect the heap with the command vmmap. That's going to print a virtual memory map of this process. And we can see from the legend at the top that the heap should be colored in blue. But there's no blue text in this output. That's because malloc won't request heap memory from the kernel until it's actually required. So we're going to use the next command to execute that next line of code. And now we've executed that first request to malloc for 9 bytes. If we follow that up with the vmmap command, we can see that now we have a heap at address hex 405000. And that heap is hex 21000 bytes long, about 135,000 bytes. Now we're going to introspect that heap memory with the viz heap chunks command, which you can shorten to viz. In fact, and I'll do my best to explain what we're seeing here. That region colored yellow is the chunk returned from that first request to malloc from 9 bytes. And we can confirm this with print a, or just pa, to check out what the return value was, the address hex 405010, which is this address here, pointing to the first quad word of user data of this chunk. First thing you'll notice is that we got more than 9 bytes. 3 quad words at 24 bytes, to be precise. Turns out that's just the size malloc will give you. If we use next, again, to request just 1 byte from malloc, or next time to request 0 from malloc, viz shows us that both times we got the same size chunk with 24 bytes of user data, so minimum size chunk. You might also be wondering what this value here is. Now, malloc data, which means that much like some stack metadata such as shared, say, base pointers and return addresses are stored on the stack itself, malloc stores some of its heap metadata on the heap. In this case, a size field. Every chunk has a size field, and it indicates the sum total of bytes that make up that chunk, including the size field itself. So in this case, 24 bytes plus 8 for the size field is hex 20. But we're seeing hex 21. Reason for that is that malloc chunk sizes increase in increments of 16 bytes. So, for example, if we use the next command to request exactly 24 bytes of user data, viz shows us that we get a chunk size of hex 21 with 24 bytes of user data. However, if we use next again to request 25 bytes, viz shows us that we get the next chunk size up, hex 30 with 40 bytes of user data. And that means the low order nibble of every chunk size field isn't used to indicate size. And that leaves it free to indicate flags. In this case, the least significant bit is set, indicating the prev in use flag, simply meaning that the previous chunk is in use. Previous chunk being the adjacent chunk in lower memory. Since all of these chunks are in use, we have the prev in use bit set in all the chunks we've requested. You might also be wondering why this first chunk didn't start at the beginning of the heap. Well, from malloc's perspective, it does. From malloc's perspective, all chunks start 16 bytes prior to their user data. And it turns out that chunk shapes, at least when viewed like this, are variable. And they depend on, for example, the size of the chunk, the size of the previous chunk, and whether either or both of those chunks are free. In fact, in the malloc source, alongside the chunk struct definition is misleading. Fortunately for us, we're only going to deal with this sort of offset chunk shape today. We're not going to have to concern ourselves with that. Lastly, I'm going to draw your attention to this region here, labeled the top chunk. Now, you recall from the output of our vmmap command that this heap is about 135,000 bytes. We're only seeing 100 or so of those bytes here. And malloc treats that remaining as yet unused heap memory as a single large chunk that it calls the top chunk. And every time we've requested heap memory, it's broken off a piece of that top chunk and given it to us. And the top chunk shrinks, is exhausted. And to keep track of how it gets a size field as well. This value here. And it isn't subject to any integrity checks. The basis of the house of force. So with that in mind, close your debugger with quit or Control D, and then we're going to run the house of force vulnerable binary. It's a small CTF style binary written in C. It's got a heap bug. To make an arbitrary write. So run the binary, have a play around with it, run it in GDB if you fancy, see if you can find the bug. And in the meantime, I'll explain what's going on. I'm going to run mine under GDB. So the first thing this binary does after printing out that little splash screen is it leaks a libc and a heap address. Now, the house of force technique doesn't necessarily require either of these. And indeed, you can use heap corruption to leak both heap and libc addresses. Today, we're going to let the binary do it for us so that we can focus on the technique at hand. Below that is a small numbered menu. Option 1 allows us to request chunks via malloc. So option 1, we'll request the chunk, and then we can send it a size, and then we can write some data to it as well. If I Control C to break in GDB and use the viz command like we were doing a moment ago, we can see that I've requested a minimum size chunk, and that I've written some capital Y's to its user data. Option 2 prints the target. Now, our objective is to leverage the house of force technique to overwrite the target, which is a short string, capital X's, that resides in the data section of this binary. This binary is non-pick, which means we know its address. Now, I know overwriting strings use the house of force to make an arbitrary write, which is a very powerful primitive, without having to dig into all sorts of peripheral exploit development stuff. If you do experience, you can drop a shell on this binary. That's what the and then drop a shell on it. In the meantime, has anybody found the bug? All right, well, I can tell you that there is an overflow on the heap. I'm using this one. We can just mic this one up if you fancy. Oh, sorry guys, I didn't realise that that mic was dying on me. My bad. All right. I'll just talk louder and shout through the microphone. Okay, so there is an overflow binary on the heap when we write data to these chunks. So, for example, if I request another chunk of minimum size, any value between 0 and 24, as we've seen, will get me a minimum size chunk. And then I fill it with a bunch of capital Y's, because why let the capital A's have all the fun? Breaking with Control C, and then viz shows us that that second chunk I requested was allocated here. I filled up those 24 bytes of user data with my capital Y input. How's the microphone? And then the last 8 bytes of my input ended up overflowing and overwriting the top chunk size field, which, as I said, isn't subject to integrity checks and is an integral part of the house of force technique. So now that we can corrupt the top chunk size field with this overflow bug in our binary, what are we going to do with it? It's a size field, so we can either make it a very small value or a very large value. Any suggestions? Interesting idea, and in fact, shrinking or increasing the size of the top chunk is a valid part of different heap exploitation techniques. However, the House of Force requires that we make the top chunk a large value, and we're going to make it the largest value. And I'll explain why in a moment. In the meantime, we're going to script what we've achieved here so that we can make it repeatable, and we can do things like send non-printing characters and do a little math. So close the binary or any debugging sessions you have open, and make a copy of the PwnTools template script. I'm going to call mine xpl.py, short for exploit.py. You can call yours what you want, except pwn.py. It's very tempting to call it pwn.py. Don't do that. First thing these scripts do is from pwn import star, meaning it will try and import itself, and the universe will implode, so I'm told. Once you've made a copy of the PwnTools template script, open it up in your editor of choice. You have a choice between Atom, available from the the taskbar at the bottom, the green icon, or Vim on the command line if you fancy. I'm going to use Vim. And this is the start of our first PwnTools script. PwnTools is an awesome little framework written by Zach Riggle that's going to allow us to do some rapid exploit development. In this case, all it's going to do is run the binary, send it some input, deal with some maths that we're going to do on the output, etc., etc. Now, there's a lot going on, but most of this is PwnTools boilerplate and some wrapper functions that I've put together to avoid this becoming too much of an exercise in Python. Fear not, we're only going to write 3 lines of Python to pwn this binary. So if you scroll down to the bottom, we're only concerned with what's between these dashed lines, which right now is some example text which we're going to delete in a moment. So that heap leak has been captured in a variable called heap, and we'll use that shortly. Symbols from the binary are available with elf.sim.symbolname, so elf.sim.target is going to be useful to us. And there's a malloc wrapper function that I've written that will be the equivalent of sending a 1 to the binary to pick the malloc option, and then its first argument will be the size, and then the second argument will be the data that we want to send it. Lastly, there's a delta wrapper function that we'll get to shortly. So I want you guys to delete all of that. And we're going to start by using the malloc wrapper function to emulate what I just did in GDB. So we're going to request a minimum size chunk. I'm going to request 24 bytes so that it's a nice little reminder for me that we're going to get exactly 24 bytes of user data. Oh, bear with me. I have a US keyboard. There we go. And then following on from that, we're going to send 24 bytes of garbage. That should fill up the user data of that chunk. We could request a larger chunk than a 201, but we might as well keep things compact for now, and that way we have to send less data. Now, anything after this, of course, is going to overflow into the top chunk size field. So we want to send a large value, and in fact, we'll send the largest value, 64-bit, all a 1-bit set. So 16F. So FF, 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 FF. And of course, we can't concatenate strings with integers in Python, so we're going to wrap all those Fs in a call to the P64 function. P64 is a PwnTools function that's short for pack64. Allows us to pack an integer as a string and deal with stuff like endianness. That way we don't have to type a bunch of \x's in, and we can deal with, in this case it's not important, but endianness when we send addresses and all that good stuff. So if everybody's got that line down, we're going to run this script. If you're using Atom, there might be a way to run your script. I'm not sure. There's also LeafPad, I think, if you're some sort of psychopath. In the case of Vim, you can use the bang./% command to run this script. Otherwise, just run it on the command line. And what PwnTools is going to do, hopefully you guys can see that, is run our binary, send the input, and then drop us into an interactive shell with it. So we can mash enter, and we'll get the menu printed out. And we can see that our script has requested one minimum size chunk for us. Well, a chunk. But that's all we can see. That's not particularly...
We just go back to the point where it executed the new script and just mistake.
Oh, sorry. Yes. Yeah, okay, so that's some PwnTools stuff that it's printing out as it reads in the binary, as it reads in the GLIBC version, all that good stuff.
How do you invoke XPL or exploit this?
Oh, I'm so sorry. Yeah, you can just do it on the command line. So from Vim, like I say, bang./%. I can't show that any better. I'm very sorry. You got it? Yeah, bang./%, as in like bang, do a command, / this directory, % in Vim is the name of this script. Otherwise, just / in the name of your script on the command line. Everyone happy with that? Awesome. So that'll drop us back into an interactive shell. We can print the target, but this isn't particularly useful. So what we're going to do is close that, and then this time we're going to run, and in fact, what I might do is just run this stuff from the command line so you guys can see. Run the script with the GDB option in capitals. Capitals is important, so to name your script space GDB, like this. That's going to do exactly the same thing. It's going to run the binary, but it's going to attach a GDB debugging session in the meantime, and then it's going to send our input. And we can Alt-Tab or Option-Tab on Mac between the binary and the debugger. So Control-C is break in GDB, and then we're going to use the viz command again, and we can see that our script did exactly what we wanted. We sent all of those capital X's or whatever you sent, 24 bytes of garbage, followed by all the F's. So now we've set the top chunk size field to a very, very large value. Great. But what use is that? Well, this is a simplified version of the output from the vmmap command that we saw earlier. Simplified process map. Typically on x86 Linux, you'll see the application at low memory, followed by the heap in a region known as the program break, then a large gap followed by the libraries, including libc and the VDSO, and then finally the stack. And what we've done by leveraging this overflow to write a large value to the top chunk size field is convince malloc that the heap is huge. So, if we made a particularly large request to malloc now, could we crash the heap into the libraries or the stack and start overwriting sensitive data? We could. If we made a particularly large request, could we wrap around the VA space and start tampering data in lower addresses to the heap? Yeah? Even in 64-bit? We can. And that is exactly what we're going to do. We're going to make a huge request to malloc that's going to be satisfied from the top chunk that malloc thinks will be able to provide this kind of memory. And it's going to stop just shy of our target, that short string of capital X's in the data section of our binary. And then the next request we make is going to overlap that target, and any data we put into it is going to overwrite it. Everyone happy with that? All right, so head back to your editor. And we're going to make that second request. So we're going to use the malloc wrapper function again. And in the size field, we're going to use that delta function that I mentioned earlier. Delta takes 2 arguments, and all it does is calculate the so-called wraparound distance between 2 addresses. So the start address is going to be the top chunk, and remember that heap leak was captured in the variable called heap, and we want to add hex 20 to that, which, because we requested a 20 size chunk, will be the actual address of the top chunk. And we want delta to calculate the distance between that and our target. So elf.sim.target, and we want to take hex 20 bytes away from that, because we don't want to overlap the target with this request. We could, but we're going to have to end up writing a lot of data to catch up with it, and in doing so, almost certainly write to an unmapped or read-only address in the meantime. Malloc's going to get away with requesting such a large amount of memory because it's only going to write to the first and last quad words of that chunk, which are both going to be mapped as writable. And then we're going to send a single byte of garbage so we can just satisfy the malloc wrapper function's signature. Is everybody happy with that? Awesome. So run this with the GDB option again. And we had a horrible death. Oh, I can't type. Bear with me. I hope you guys didn't copy exactly what I did because it was wrong. I forgot to close a bracket, didn't I? And I should have removed that. My apologies for wasting your time. Delta takes 2 arguments, that heap, I shouldn't have closed a bracket after heap plus hex20. Once you've made that correction, run this under GDB again. This time it's happy. We can alt-tab to the binary, mash enter a bunch of times, make sure it hasn't crashed, which is good, since we're requesting chunks now with a corrupted top chunk size field. And don't use the viz command at this point. Homebag will have a right meltdown. Instead, we're going to dequeue for dump quad target. And this is the target address, hex 404010. And we can see there those capital X's represented by hex 58 values. If we dump quad target minus hex 10 or minus 16, we can see the two quad words leading up to the target with this suspicious value here. Now if we print main underscore arena.top, now we're going to get into what arenas are with our next technique, but for now, please take my word for it that this prints the address that malloc thinks the top chunk resides at, which is hex 404000, right here, making this the top chunk size field. So now the top chunk is sat right before our target data, and the next request we make, the first quad word of that should nicely overlap target data. And in fact, we can do this manually. If you hit C for continue, head back to your binary and make one more request of minimum size. Any data that you send will end up overlapping the target. And you can check the target with option number 2 and see that you've successfully overwritten it with whatever data you wrote there. But we might as well just add this to our exploit. So you can make one final request using the malloc wrapper function for any amount of data. And then any data that you send, so in my case, just a much win string, that request is going to overlap our target. And then you can just run this without the GDB option and check the target with option 2. And that's all there is to the house of force. In summary, we leveraged an overflow into the top chunk size field to make it a very large value, tricking malloc into thinking that the top chunk was massive. Then we made a large request to span the gap between the top chunk's current position and our target, which happened to be in the data section of this binary. So it was able to wrap around the VA space to do that. That meant that the last request we made overlapped our target, and we were able to write arbitrary data to it. Simple as that. So before we move on to our second technique, are there any questions on the house of force? Awesome. Did everybody get that down? Just briefly, for those of you for whom it's not working, or if I've made some horrible typos, there is a .file, .pwntoolsolution-target in this directory that does exactly what we just did. Sorry, it's at the bottom of the screen. .pwnTools_solution-target that does exactly what we just did, and it's got a bunch of comments as well. So if you were unable to get that working, we'll crack on for time purposes, but you can edit that and read the comments and check it out later if you fancy. Okay. All right, let's move on to our second technique, the fast bin dupe. Now, one of the things that the heap is better at than the stack is dealing with or recycling unused memory. And this is achieved via the second of malloc's functions we're going to look at today, free. And free is another dead simple function. All you do is pass it a pointer to a chunk that you no longer need, and then you can forget about it, safe in the knowledge that that chunk will be recycled if and when is necessary. From malloc's perspective, however, that chunk is going to be eventually linked into one of several free lists, which are, as they sound, lists of free chunks. Of interest to us today are a collection of these free lists known as the fast bins. Fast because the free chunks in them are recycled fast, and bins because that's what the malloc maintainers like to call lists when they feel like it. And the fast bins themselves are just a small collection of singly linked, non-circular lists that each hold chunks, free chunks, of a specific size. And to help us visualize how the fast bins work, we're going to debug another small demo binary. So switch fire back to your VMs, and this time navigate to the fast bin dupe directory. And once more, we're going to debug the demo binary under GDB. Once GDB is started with GDB demo command, we're going to break main again to set a breakpoint on the main function, and then we're going to run it with run. This time we can see the first thing this binary does is request 3 minimum size chunks using malloc. We know exactly how that works, so next 3, like this, is going to execute those lines, and then we can use the viz command to show that the heap is in exactly the same state as we'd expect, with 3 minimum sized hex 20 chunks. Next thing this binary does is free those 3 chunks in order, A, B, and C, or green, yellow, I want to say turquoise, and then purple. And the head of the fast bins that I talked about resides in a memory region called the main arena in libc's data section. Now, arenas are just where malloc stores its non-inline heap metadata, and the main arena is the arena for the default heap, the one we're using. Fortunately for us, we don't have to manually introspect main arena memory. We can use pwnbag's fastbins command, the output from which tells us that there are, under default conditions, 7 of these fast bins, these 7 singularly linked non-circular lists. And each of them hold 3 chunks of a specific size. So there's a 20 fast bin that holds chunks of size 20, 30 fast bin, etc., all the way up to 80. So let's use the next command to free that first chunk. Now a combination of the fastbins and viz commands are going to show us that that first chunk at hex 405000, remember that malloc considers chunks to start 16 bytes before their user data, so that chunk starts here, according to malloc. That first chunk has been freed into the 20 fastbin. And all that means is that its address, hex 405000, has been written into the 20 fastbin slot in the main arena, somewhere in libc's data section. So let's free the next chunk with next. Now we've freed chunk B. The fastbins and viz commands are going to show us that now chunk B, the I'm going to say turquoise chunk, has been linked into the 20 fastbin, and it's at the head of the 20 fastbin. Fastbins are last in, first out, or LIFO structures, meaning that every time we free a chunk into one of these bins, it's going to be written to the head of that bin. So there's one slot in the main arena for each of these bins. Now the address of chunk B, that turquoise chunk, has been written into that slot. But there's no more space for the rest of the metadata for this list in the main arena. Like I said, there's one slot. And the rest of that data is held on the heap itself in line. And we can see that the first quad word of user data of chunk B has been repurposed by malloc as a forward pointer, or FD. And that points or holds the address of chunk A. Chunk A's FD is null, indicating the end of the list because it's a non-circular list. And malloc can repurpose up to 6 quad words of user data of a chunk every time it's freed. So we're going to free the next. We're going to free chunk C with next, and then fastbins and viz shows us that, as we expect, chunk C is the head of the 20 fastbin. Chunk C's FD points to chunk B's address here. Chunk B's FD points to chunk A, and chunk A's FD is null, indicating the end of the list. So last in, first out. And we can see that pwnbag has annotated this to the right-hand side as well. So fastbin 0, 1, and 2. So I said they were last in, first out structures, meaning that if we use next 3 to execute those 3 further requests to malloc for minimum size chunks, viz is going to show us that despite the fact that we've now requested 6 chunks of minimum size, we still only have 3 on the heap. Fastbins is going to show us now the 20 fastbin is empty. Those 3 chunks got allocated from the 20 fastbin, so the fastbins take precedence over allocating from the top chunk because they're faster. And if we use print D, print E, and print F, we can see that we got the user data addresses of those 3 chunks back in reverse order. So chunk C was the last one to be freed, and therefore was the first one out of that fastbin. So we got chunk C, then we got chunk B, 405.030, and then finally we've got chunk A again. We've got those user data addresses. So if everybody's comfortable with how the fast bins work, we're going to start messing with our vulnerable binary. So close your debugging session with Control-D or quit, and have a play with the fastbin dupe binary. And once again, a small CTF-style binary written in C. This one has a different type of heap bug that we're going to leverage the fastbin dupe technique against for another arbitrary write. So have a play with it. Again, run it under GDB, see if you can find the bug this time, and in the meantime, once more, I'll explain what's going on. So I'm going to run my binary under GDB. And the first thing it does is leak a GLIBC address. We're not going to use that, but we'll come back to it when we're dropping shells on these binaries. Or, like I say, if you're into your exploit dev, you can use that leak now to drop a shell on this binary. After that, it requests a username. For now, we're going to type any old garbage into that field, and we'll come back to that later. Our little menu allows us to request up to 7 chunks this time. So option 1. However, the size field is limited to fastbin size chunks only. So 120 bytes of user data maximum, that will give us an 80 size chunk. So I can request a minimum size chunk again and send a bunch of data to it. Option 2 allows us to free these chunks by index, starting at 0. You can't free incorrect indices, so I can't free index 1 because I only requested 1 chunk. Sorry, I can't put this any higher on the screen. But I can free index 0, like that. Option 3 prints a target again. Once more, our objective is to overwrite that target, that short string of X's in the binary's data section. So, has anybody found the bug? Well, this time, there's a different type of bug called a double free, which allows us to free the same chunk twice without allocating it in between. Now, that sounds kind of benign, right? But freeing the same chunk into the same fastbin twice without allocating it in between is going to write that chunk's address to that fastbin twice, meaning that it might be allocated for 2 different purposes simultaneously. So, for example, if this program were to allocate a chunk to hold an admin password hash, for example, it might also allocate that chunk simultaneously, if it's been double free, to us, the user, to hold some benign user data. And we might be able to leverage that situation to read or write to that admin password hash. So let's try that now. If you request a chunk of any size, write some data to it, and then attempt to free it once, and then free it again, what happens? We get an abort. It turns out that the GLIBC maintainers are wise to this. They know that double frees are dangerous. And there is an exploit mitigation in the fastbins as part of the free function. And that mitigation works thus. If you free a chunk into a fastbin, and that chunk is already the head of that fastbin, so it was the last chunk to be freed in, then that's clearly a double free scenario, abort. So are we scuppered? Or can anybody think of a way around this little protection? Any suggestions? Precisely, yeah. We just free a different chunk in between. It's that simple. So if you run the binary again, request a couple of different chunks, as long as they're the same size. So I'm going to request 1 chunk of minimum size and another chunk of minimum size. And then I'm going to free chunk 0, like I did before. But instead of freeing it again straight away, I'm going to free chunk 1. Now I'm going to double free chunk 0. And the binary doesn't complain. Simple. So we bypass that first double free exploit mitigation by, as your man said, just freeing a different chunk in between. So let's script this up. Once more, make a copy of your pwn-tools template Python script, and then open it up in your editor of choice. Not like that. Once again, do we have ambient music in here? That's really put me off. All right, let's just crack on. Definitely not coming from any of my devices. So this time our script is going to set the username field for us. And it's just going to send 16 capital Ys, 16 bytes of garbage. Like I said, that's just to sort that field out. We're going to come back to that later. And this time we have a malloc wrapper function that works just like before with the size field followed by whatever data you want to send. This time there's no overflow. So if you request 8 bytes, you can only send 8 bytes. If you try and send a bunch more, you're just going to see that menu get printed out a bunch and you know something went wrong. This time we also have a free wrapper function. So we can free 0, free 1, and that will free indexes 0 and 1. So delete all that stuff. That's why we made a copy. And once more, we're going to emulate what we just did in GDB. So let's request our 2 chunks. I'm going to use minimum size chunks. You guys can request any fast bin size chunks you like, as long as they're the same size. So I'm going to use malloc, and I'm going to use I'm going to request 8 bytes for a minimum size chunk, and I'm just going to write 8 bytes of garbage. And then we're going to do that again. I'm just marking them up with some A's and B's so that we know where they came from. And then we want a free chunk 0, followed by chunk 1, and then chunk 0. Once you guys have got that sorted, run your script with the GDB option. Look up when you're done typing as well.
We need that user interaction thing before these mallocs or...
Thank you for pointing that out. Yes, we do. I've got ahead of myself. If you can't just mash the undo button, which is you in this case, and get back to this state, and then quickly correct it all, then just make another copy of the file. Thank you for pointing that out, Saul. Yes, we need the... All right, there we go. Should look more like this. We need to do the username interaction, as you said. Then we're going to request our 2 chunks, followed by freeing them. Glad someone pointed that out before I got really confused and just sort of let it crack on. Okay, my apologies. All right, once you guys have got that written down, run your script with the GDB option. We can alt-tab to the binary and see that that works. And then Control-C to break in GDB. Well, that's just gone off the screen a little bit. So be it. Right, now we're going to use the viz and fastbins command to once again introspect the heap and the fastbins. And we can see that we've got different addresses this time. That's because when you attach with GDB, using the pwn-tools GDB functionality, everything's going to be subject to ASLR. So even though it's not really a drama with us, what you can do is run your script with the no ASLR option. So just like you did GDB in caps, so run the script, GDB, no ASLR, all caps. You don't need to use this, but it just makes debugging a little bit easier. And then once again, Control-C to break, and then fastbins followed by viz. And we can see now that the addresses are kind of back to what we're used to, and we can just run it without the no ASLR option when we want to do this in production. So chunk A is linked into the 20 fastbin to begin with at the head, hex 405000, followed by chunk B, or 1, I suppose I should say, chunk 0, then chunk 1, a hex 405020. But as you can see from the viz output, chunk B's FD points back to chunk A, and vice versa. So now we've turned, by leveraging this doing this double free, we've turned a singly linked non-circular list into a circular list. It's going to keep giving us these 2 chunks back. Now, Unfortunately, the example I gave you is pretty useless in this scenario. Like, we don't have any admin password hashes on the heap. We control all the user data. There's nothing useful for us there. Instead, what if we requested chunk 0 back to us so that we could manipulate its user data? We can write arbitrary data to these chunks, but also kept it in the 2.0 fast bin simultaneously, where that first chunk, that first quad word of its user data is being used as a forward pointer. Then, if we can overwrite that forward pointer, because we can legitimately write to this chunk, having allocated it back to us, we might be able to link in a fake chunk into this 2.0 fast bin, perhaps that overlaps the target, and then request that fake chunk back from the 2.0 fast bin and write arbitrary data to our target. So let's give that a go. If you close your debugging session and head back to your script, we're going to make a request using the malloc wrapper function for 8 bytes, so we can cover that first quad word. And we are going to pack64 elf.sim. This time we're going to use user. Now, in this binary, there is a user struct that contains the target. That's why we're using user. PwnTools doesn't cope with structs very well. Either that or I just can't use PwnTools well enough. Probably the latter. Either way, elf.sim.user is the address of the user struct, which happens to start 16 bytes before the target address. So that's what we want. We want that malloc address 16 bytes before the value that we want to overwrite. And also, we'll see that our username is the first part of that struct, which I'm sure will become clear. So once you've got that sorted, run the script with the GDB option and no ASLR if you want to have those comfortable addresses again. Break with Control-C. And now the fastbins command is going to show us that we've corrupted that fastbin linked list to this address hex 404010, which we can view with dump quad ampersand user to see hex 404010. That's our username there, 16 bytes of capital Ys, and this is the target, those capital X's followed by a null byte, hex 404020. So we've linked a fake chunk into the 2.0 fastbin by overwriting one of the forward pointers. So all we need to do now is allocate out these two rogue chunks here, the chunk 1 and chunk 0, as we called them. And then the third allocation that we make from the 2.0 fastbin will be a fake chunk overlapping our target, and then we can just write arbitrary data to it. Easy. So let's script that up now. We want to make another 2 requests to malloc for minimum size chunks. So again, I'm just going to write 8 bytes. Like that. You can copy paste what you had above there as well for the sake of speed, and then run it with the GDB option again. Break with Control-C. And now fastbins command shows us that the next chunk we're going to allocate overlaps the user struct and should be able to overwrite our target. Simple. So let's try that manually. If you C for continue, Alt-Tab back to the binary, and then make your last request of minimum size. And unfortunately, we get caught out a second time. If you can read that, it says malloc memory corruption. And we've been hit by a second exploit mitigation in malloc. This time, it's a little more insidious. This malloc corruption fast doesn't really give us much of a hint as to what's going on. Turns out there is a size field check when requesting chunks from the fast bins. And malloc's just going to check to make sure that that chunk size makes sense. If you're allocating a 5.0 or a hex 2.0.0 chunk from the 2.0 fast bin, that doesn't make any sense, so it's going to abort. So if you head back to your editor, in fact, I tell a lie, don't go back to your editor. Run another debugging session. And this time, dump quad ampersand user. And as we saw before, we are in the lucky position of controlling some of the data prior to our target. So we're going to forge a fake size field to trick malloc into thinking this is a legitimate chunk that we've linked in. So now head back to your editor, and we want to mess with that username field at the beginning of this script. So instead of writing 16 bytes of garbage, we're going to write 8 bytes of garbage. And then we're going to use pack64 hex 21. Once you've done that, debug it again. And this time, dump quad ampersand user is going to show us that we forged that fake size field, hex21. Now, this is lab environment, so we happen to have control of the quad word right before our target, which is pretty convenient. But remember that fast bins go up to size hex 80. So we could scroll back by up to 120 bytes before this. And as long as we could coerce a size field to anchor this fake chunk in, we can manipulate potentially data up to 120 bytes after that. So now we should be able to manually continue, Alt-Tab back to the binary, and this time request a minimum size chunk, and we don't get a crash. And any data you write in here should overwrite the target. And if we want, we can make that last request to malloc in the script as well. I apologize if this is getting close to the bottom of the screen, incidentally. So once you've made that last adjustment, you can run the script without the no ASLR stuff and without GDB to make sure we're legitimately nailing this down. And then option 3, print the target, should just print whatever text you decided to write there. Awesome. So that's all there is to the fast bin do. Once again, if you guys had an exploit that didn't work there is another .file, .pwntool solution target that will do exactly what we've just done, again, with a load of comments on it. How are we doing for time? 2:30, 3:30. Fantastic. All right, so before we move on and start dropping shells, does anybody have any questions on the fast bin dupe technique? All right. How are you guys coping? Not too tired? Yes. So that's the length of that much win string. In this case, as I mentioned earlier, you have to request what you want to write. If I wrote a 1 there, it would receive the M, and then it would send the U to the menu, the C to the menu, etc. So yeah, in this case, we have to specifically request that amount. So I just requested 9 bytes. I could have requested more and then written less as well. All right, so let's revisit the House of Force, and this time we're going to drop a shell. So navigate back to the House of Force directory, and I suggest making a copy of your exploit script. As I mentioned, if your exploit script didn't work, there is a pwntool solution target script that you can use instead. It should be almost identical to what we've done. I'm going to copy my xpl.py script and just make a backup of it. And then once again, open your exploit script in your editor of choice. And we're going to delete everything after that first request to malloc. Now, that first request to malloc we're going to keep because that's what set up our House of Force primitive. So we used that to request a minimum size chunk. We filled up that minimum size chunk's user data with garbage, and then we overwrote the top chunk size field with a large value. So now the next request we make can be really large, and we can use it to catch it up to something useful in memory that's going to allow us to hijack the flow of execution. Any suggestions as to what that might be? Anywhere in this binary, in this process's VA space? Anything that overwriting it will allow us to hijack the flow of execution? Any suggestions? Got POT entries, yeah. Anything else? All right, well, let's think this through. We could clobber return addresses on the stack, for example. But in this case, the stack is subject to ASLR, and we haven't leaked it. So the stack's out of the question. We could attack the binary. We know it's not pick, so we know it's address. And we've already managed to overwrite a target quad word there already. However, this binary was compiled with full railroad, which we can check with checksec, and then the name of the binary, which shows us that it was indeed compiled with full railroad, meaning that got POT entries and not exit funcs. Yeah, essentially detours list that I'm forgetting for some reason. Both of those are compiled with both of those will be marked read-only by the time that the program is initialized. So unfortunately, the binary is out of the question as well. FiniArray is what I was thinking of. Got PLT and FiniArray are out, but we've leaked libc in this case, and there's plenty in libc. libc has a GotPLT. There are exit funcs and TLS detours as well to target. However, libc's GotPLT doesn't have anything that we can reliably invoke with this binary. And unfortunately, exit funcs and TLS detours are protected by pointer mangle, which means that unless we had an arbitrary read, we couldn't reliably tamper those values. But it turns out there is a malloc-specific way of hijacking the flow of execution. I'm talking about the malloc hooks. Every one of malloc's core functions, so malloc, free, realloc, and more core, etc., have an associated hook. And they're typically for the purpose of developers hooking the malloc function and creating their own memory allocators or trying to collect statistics on malloc. We're going to use them to hijack the flow of execution. And I'll explain how how all of malloc's hooks work momentarily. But if you go back to your editor, we're going to use the malloc wrapper function to request the large chunk, so leverage our house of force primitive. And this time we don't need delta because we're not wrapping around the VA space. So we want the distance between libc.sim. And then the malloc hooks. The malloc hooks symbol is __malloc_hook. And the reason we're using the malloc hook is because malloc is the only function that we can reliably call out of libc's out of malloc's core functions in this binary. We can do malloc and that's it. No free or no realloc or any of that good stuff. And of course, just like before, we want to stop hex 20 bytes just shy of that malloc hook, so the next chunk that we request is going to overlap it. And we want the delta, or the distance between that value and the heap plus hex 20, just like we did last time. And we're going to send a byte of garbage just to satisfy the malloc wrapper function's signature. So we're going to make that large request, which is going to cover the space between the heap's top chunk and the malloc hook. Once you guys have all got that down, once again, run this script with a GDBR and, if you want, a GDP and no ASLR options. All right, well, we didn't get a crash, which is a good start. Control-C to break in GDB. And what we want to do is dump quad ampersand __ malloc _hook. And the malloc hook resides at this Charlie10 address here, and it's currently null. So once malloc's done with its initialization routines, the malloc hook is going to be null. And the way these hooks work is that when they're null, they're in a benign state. They're unused. Any call to malloc will be forwarded to the malloc function. But as soon as we write a value to the malloc hook, then any address that we write there will be executed instead when malloc is called. And if we append a -2 to that malloc hook command, we can see a suspect value here, and another call to print main _arena.top shows us that this 8 Charlie00 address is where malloc thinks the top chunk is, making this the top chunk size field. So we're ready to overwrite the malloc hook with an address of our choosing. So once you guys have done looking at that, we know that the next request we want to make, we might as well make it for a minimum size chunk, so any value between 0 and 24. And what we're going to do is just test this theory. So we're going to pack 64 hex deadbeef, which should be an unmapped address in pretty much all scenarios. So we're going to use this house of force primitive to overwrite the malloc hook with the address deadbeef. Now when we request any malloc calls after that, we should bang into this unmapped address. So run that with the GDB option. And just straight away, Alt-Tab to your binary, and then make a request to malloc. It looks like the binary is hanged, and we can see if we Alt-Tab back to GDB, we got fault address at deadbeef. And we can see that the instruction pointer holds the value deadbeef, which means we've hijacked the flow of execution. So now all calls to malloc will be proxied out to whatever we want it to be. So does anybody have any suggestions where we go from here? What do we want to execute? We can go anywhere in libc, anywhere in the binary, anything we want. Well, a good option is always system. For those of you unfamiliar with it, libc's system function takes a pointer to a string, and that string is treated as a shell command. So we could run a shell, we could run netcat reverse shell, whatever we wanted, bin cat flag if we were doing a CTF. So system is a really good option in this. It's kind of a CTF-y choice, but that's what we're going to do. So close your GDB session and head back to your script and replace hex deadbeef with libc.sim.system. Now when we run this on the GDB, libc.sim.system, breaking in GDB with Control-C, and then print __malloc_hook, shows us that now the malloc hook holds the address of libc's system function. So every call to malloc will be the equivalent of a call to system, which is great because system takes a single argument and malloc takes a single argument. So all we have to do now is somehow pass the string we want to execute, or the string we want treated as a shell command, which in our case we want to drop a shell, so /bin/sh, to malloc. Any suggestions as to how we're going to do that? Well, there's a couple of ways. I'm a fan of using the bin/sh strings already available in libc. What I didn't mention was how system actually works is it forks the process and then executes the equivalent of execv bin/sh to run a subshell, and then your command is executed within that, which means the string bin/sh resides somewhere within libc. So if we send the address of that bin/sh string masquerading as a size field to malloc, it will become the equivalent of, instead of malloc large size, system pointer to the string bin/sh. And hopefully, we'll get a shell. So if you head back to your editor, we're going to make one more request to malloc. We can't do this one manually. And in fact, I tell a lie. The malloc function is going to do things like expect the data prompt and the sort of new line prompt here. So PwnTools does have timeout options on those functions, but we're just going to get this done as quickly as possible. So instead of making a call to malloc, which will hang, we're going to use io.send, which just means send the following string to the binary. We're going to send a 1 to pick the malloc option, and then we're going to use io.send after, and the first argument of that is going to be the size prompt. So quotes size : space, comma. Send after it will wait for the size prompt and then send what we want it to. The reason we're using send after instead of just another io.send is because Python can get a little bit enthusiastic, send these two lines straight back to back, and then the binary is not going to be able to tell the difference between our inputs. It's going to think we tried to send a very large menu option. So once we've sent our size field, we want to send, and you can wrap this next bit in str, if you like, or you can use a Python format string like this. Either way, we're going to use libc.search and then the string bin/sh, if I can type. And then you can either tack a call to next on the end of that, or you can just wrap the whole libc.search in a call to next to get that next iterator. All that's doing is searching libc using PwnTools for that string bin/sh, which, as I said, occurs a couple of times in libc naturally. And since we've leaked it, we know its address. And then we're going to send that as a size field to malloc. And since we've overwritten the system, since we've overwritten the malloc hook with the address of system, it should become system bin/sh and drop a shell. So let's cross our fingers, and we'll run this just on its own without the GDB or no ASLR options. And it looks like the binary is hanged, but we have a shell. Easy. We have another option. Any other suggestions as to how we could drop a shell or run a command that we want? Well, we've leaked a heap, and we can write any data we want to the heap. So instead of finding that bin/sh string in libc, we could, instead of 24 bytes of garbage when we make that first request to malloc, we could write the string bin_sh there with a null terminator. And then instead of 24 bytes, just write 16 bytes of garbage. And then we can use io.sendAfter, to send the address of the heap plus hex 10, which is the address of the first quad word of user data of the chunk that we requested at the very beginning, which has our string bin_sh. And that should also be an alternative way of dropping a shell. There we go. And that's all there is to dropping a shell with a house of force. So to summarize, we set up our house of force primitive, and then this time we used it to overwrite the malloc hook, which allows us to redirect execution every time malloc is called. We pointed the malloc hook at system, so all future calls to malloc became calls to system. And then we grabbed the address of the string /bin/sh, which exists naturally in libc, or we could have written our own, netcat reverse shell or bincat flag, etc. command onto the heap, and then sent the address of one of those strings to malloc masquerading as a size field, and that executed our command. Before we wrap this up with our last shell, are there any questions on dropping a shell with a house of force? All right. Again, if I'm moving too fast, there is a .pointools solution shell script in that directory that will do exactly what we just did with a bunch of comments. So if you want to revisit it later, it should be reasonably clear what's going on. Okay, last one. Navigate back to the fastbin_dup directory. And this time we're going to drop a shell using that fastbin_dup technique. Once more, make a copy of your exploit. And again, if you weren't able to get that working, you've got your pointools solution target script to use instead. Open your copy in your editor of choice. This time we're going to delete everything after those 3 calls to free. The script is still going to deal with our username fields. It's going to request 2 minimum size chunks, the same size, and then it's going to free them alternately. So we've already got our fastbin_dup primitive set up. And again, the question becomes, what are we going to overwrite with it? So this time we might as well try the free hook, since this is a full railroad binary as well. Free hook, if you can get to it or you can use it, is a much better option than the malloc hook typically, because if you overwrite it with system, freeing a chunk is the equivalent of calling system with a pointer, with an implicit pointer to your user data. So you can do just like we did a moment ago with the house of force technique, but you don't need to leak the heap, because freeing that chunk would have implicitly been a call to system bin_sh. So how we did this last time was we used the malloc wrapper function to request 8 bytes, and this was going to request our double free chunk back from the 2.0 fastbin, and it was going to overwrite its FD so that we could link a fake chunk into the 2.0 fastbin. And we want to link pack64, just like we did before, libc.sim.__free_hook. And we want minus hex 10 on the end of that, because in the fastbin_dup we need to use malloc's addresses, so this way the free hook will become the first quad word of user data of our fake chunk. Once you've got that, run this with GDB, with the GDB and no ASLR options. Control C. Whoops. And we are going to use the fastbins command. And as we've expected, we've linked some sort of libc address into the 2.0 fastbin. We can use dumpquad __free_hook to look at the free hook, which is this 588 address here, this quad word, which is null, as we expect. And again, we can append a -2 to that to introspect the memory around the free hook. And you can see that we've linked in this hex 578 address to the 2.0 fastbin. Does anybody see a problem with this technique? Bearing in mind what we had to do to actually allow malloc to allocate a chunk here. What's missing from this quad word? Yeah, the size field. We need to coerce a size field into this value here. Now, last time we did that by having the luck to have control over that data right before the target data that we wanted to control. But in this case, all of this data resides in libc's data section, which means we can control little to none of it. But remember that we can allocate fake chunks up to hex 80 size in this binary. So if you scroll back 16 bytes and then print 16 quad words and then print 18 of them, that 588 address is where the free hook resides, down here. And this is as far back as we can get an 80 chunk size. And it's nulls all the way down, unfortunately. And there's nothing we can do about this, at least not right now. So let's have a look at the malloc hook. If you do that same command, but swap out free with malloc, so malloc underscore hook minus 16, 18, like that. The malloc hook resides here at this Charlie10 address, and we can see that there's a little more to it this time, but nothing as useful as a naturally occurring perfect 80 size field up here, or like a 40 here, or anything like that, sadly. But there are some more values, and these are reasonably consistent values. This value right here, this value here is the standard in IO-wide data vtable pointer. And standard in is really hard to get rid of. Even if the first thing with this binary did was close standard in, and there was never any data read on standard in and never anything printed out on standard out, all the standard ins, all the standard IO infrastructure still exists. It's a very reliable thing to have. This quad word here is a padding quad word. And these, I believe, are the memoline hook and the realloc hook. So they may or may not be the values that we see here. Now, unfortunately, there's no naturally occurring size fields, but it turns out malloc makes some assumptions about the chunks it's allocating, at least from the fast bins. The free function will ensure that any chunk that you pass to it is 16-byte aligned. And therefore, malloc has no reason to check the alignment of chunks that it's allocating. So that gives us a kind of scrolling window into this data here that we might be able to coerce a chunk size field out of. Now, these are all subject to ASLR, but ASLR doesn't affect every single bit of every address. For example, the low order 12 bits of every address won't be subject to ASLR because ASLR only works at a page granularity. Also, on x86 Linux and most Unix systems, the three most significant bytes will be 00007F. If you have a MacBook, you can open a terminal and type vmmap $, and that will print out the virtual memory map of the process you're using right now. And you'll see under all of the libraries are loaded at these 00007F addresses. So these bytes are constant in Linux, at least. So if we scrolled back from the malloc hook here, hex 20 bytes to here, and then another 3 bytes would capture the 3 most significant bytes of this value here, followed by the 5 least significant bytes of that standard in vtable pointer, which, as I said, will almost certainly occur in your C program or C++ program. Then the next quad word that forms the size field, or that forms a size field in this alignment, will have 5 nulls from the low order bytes here, followed by null, 7F. So we can test that. We can dump quads, ampersand, malloc hook. In fact, I tell you what, it's easier to do dump quad 0x and then use the malloc hook address, so we don't have to cast it as a car or anything mad like that, minus hex 23. And we can see that because of the little endian nature of the system, we can coerce a reliable 7F size field out of this. Now, we haven't seen 7F as a size field, and that's because it will never naturally occur. That fourthly significant bit isn't used for anything, and those flags don't make any sense. But again, malloc makes some assumptions about the state of the chunks that it's allocating. And we can mess with these flags quite a lot because it ain't going to check them. We can have 7.0, 7.1, 7.2. The only thing we can't have is the thirdly significant bit, which represents the non-main arena chunk, or non-main arena flag, without the secondly significant bit, which represents the isMmapped bit. Without digging too much into what they are, basically, if you have the non-main arena flag set on a chunk, malloc will go looking for a non-existent arena and your segfault. Unless you have that isMmapped flag set, in which case it'll ignore it and it won't go looking for it. So you can't have 5, for example, but you can have 6 and 7. And 7f, it turns out, works just fine as a 7-0 chunk size. So, if we go back to our script, and instead of minimum size chunks, we're going to start requesting 7-0 size chunks. Easiest way to do that is to get the chunk size you want and take 8 off of it. So hex 68 is going to give us the maximum user data for a 7-0 size chunk. So change those first 2 requests to malloc to request hex 68 bytes. You can keep the data that you sent. And then once it's freed, make sure that the chunk that we request to overwrite the free hook with is also a hex 68 or hex 70 size chunk. Once you've done that, run it under GDB. Control-C to break. And the fastbins command is going to show us what we've linked in. And what I've forgotten to do is change this value here. We want libc.sim.malloc hook, because we want to change that out from the free hook. And we want minus hex 23 this time. So we want to write the address of malloc hook minus hex 23, and I've got break there as well. Once you've made that adjustment, run it with GDB, Control-C, and now if you capture that address that we've linked in to the 7-0 fastbin now, and use the dump quad command, we can see that that's set up a 7f size field nicely. And you can take off the no ASLR option and run this all you want, and that 7f size field will stay constant. So now what we want to do is simply allocate out those 2 other chunks that we had, so chunk 0 and chunk 1 and chunk 0 as we called them earlier on. A little bit like this. So 2 more requests. And then the next chunk we request, and you can copy the request for hex 68 size bytes from earlier. Now sets us up so that the next 7-0 size chunk we request is going to overlap the malloc hook. So let's make that overlap work for us. We're going to request another 68 bytes of user data and do just like we did before. pack64 libc.sim.system. I'm going to remove the no ASLR option from my command line to make sure this works in a production environment. Once you've written the address of system over the malloc hook, and that isn't going to work, is it? We need to write hex 13 bytes of garbage to catch up to the malloc hook. Bear in mind that those 13 bytes of garbage are going to overwrite the memoline and the realloc hook that we saw earlier on. So you've got to start being careful at this stage of the game. We're not going to trigger either of those, but functions like printf can end up triggering realloc when they resize buffers. So once you've done this, either you manage to write nulls to those addresses or you start being very careful as to what kind of functions you call. Once you've done that, run it with the GDB option, break, and we're just going to print __malloc_hook. And now we can see that we've, once again, managed to overwrite the malloc hook with the address of system. Unfortunately, we can't do what we did last time. We were able to send arbitrarily large requests to malloc before, but if you recall, this time we're limited to 120 bytes, and that's not a usable address that we can stick in there. So does anybody have any suggestions as to how we're going to crack this final step and drop a shell? or we could use a one gadget. For those of you unfamiliar with one gadgets, they're just pieces of code that exist in libc naturally that do the equivalent of execve bin sh. I mentioned that what system did was fork run execve bin sh. Let me get that back. And then in that subshell, run your command. So the string, the code, execve bin sh exists in libc. And a chap called David942J has written a really good one gadget finder. It's called one_gadget. It's the Ruby finder. There is a Python version out there that wasn't written by him. It ain't very good. Use David942J's Ruby one gadget finder. And all we have to do is, and you guys don't need to copy this bit if you don't want to, because this path is a little bit obscure. But we're going to point the one gadget finder at the version of libc that we're using for this example. And what it will do is print out the offset of every equivalent of execve bin sh it finds in libc. And then it will print the constraints as well. And what you can do is tell the one gadget finder to run your script and try every single one of these offsets one by one until it finds one that works. Save us doing that. I can tell you that this last one at the bottom here, hex E3AAB, is the offset of a functional one gadget that's going to work with the constraints that we have, that the stack pointer plus hex 50 will be null, which it always will be by the time we get to hitting this gadget. So if you go back to your editors, and instead of libc.sim.system, we want libc.address plus hex E3AAB should be the address of the one gadget. So now we're set up to proxy all future calls to malloc to a piece of code in libc that should run the equivalent of execve bin sh. So if you run this script, again without GDB this time, so we've got ASLR, the binary should just work as normal, but the malloc hook's been overwritten. So if we request a chunk of any size, it looks like the binary is hanged. But once again, we get a shell out of it as that one gadget executes. And that's all there is to drop in a shell with the fast bin dupe technique. In summary, we double freed a hex 70 size chunk this time by dodging the fast bin's double free check by freeing another chunk in between. And then we overwrote the FD of one of those chunks by requesting it back to us so we could legitimately overwrite its user data. We overwrite the FD of that chunk with a pointer to an address just below the malloc hook where we can coerce by slightly misaligning our chunk, which malloc's going to let us do, a reliable 7F size field. And because malloc has a bit of slop in the numbers that it allows as size fields, we can allocate another 70 size chunk there and use that to overwrite the malloc hook with the address of a one gadget. And then every call we made to malloc was the equivalent of execve bin sh. Before we wrap things up, are there any questions on dropping a shell with the fast bin dupe technique?
Why there is just slack? That's a design that is slack. For example.
Yeah, essentially you want speed, right? This is a memory allocator, and as I said, it's used with everything. So a lot of the malloc maintenance stuff, there's essentially Florian Weimer who helps maintain malloc in GLIBC. He does the security stuff. Everyone else tries to make it faster. And yeah, so you could have, it's the classic security speed trade-off, essentially. So yeah, the assumption is that, for example, the alignment has been done by free. There should never be a scenario whereby a chunk has gotten into the fast bins without it being freed legitimately by the free function, and therefore having a sensible size field because the free checks are much more fastidious than the malloc checks.
Is that different depending on the architecture you're running?
No, this is just C code, right? So yeah, the one gadget is libc dependent, but everything else we've done is manipulating a higher level concept of how the malloc engine works, essentially. Yeah, so this is all just C code, essentially. All right, well, I've just got a couple of words on like relevance, and then I suppose we can wrap it up. We are a little bit early, but it's also very warm in here. So if you weren't able to get that working because I went a little bit fast, again, there is a .pwnTools solution shell script there so that you can check that out later. It does exactly what we did again, but with a bunch of comments. And the eagle-eyed of you will have noticed that the versions of GLIBC that we were using today were 2.28 and 2.29, which are the two latest versions. 2.30 dropped last month, but it's not in circulation yet. Ubuntu 18.04 long-term support is using 2.27. Most stuff is behind that. I think 19.04 is using 2.29. Well, we were using 2.28 and 2.29. They had a small modification which removed something called the T-cache from malloc. And the T-cache is an attempt by the GLIBC maintainers to catch malloc up to fast implementations like JE-malloc. And it is essentially the fast bins, but without any protections. The reason I removed the T-cache from these versions of libc is because it would have been pointless teaching it because it's so easy. Heap exploitation now is easier than what I'm teaching here. Like I said, T-cache bins are... You can double free a T-cache bin without the double free check and without the size check. Even in 2.29, they implemented a double free check for the T-cache. It's still just as easily bypassed here. GLIBC 2.29 implemented a check that does mitigate our first technique, the House of Force. 2.29 was released late last year. Like I said, it is not really in circulation on many of the common distros yet. It's certainly none of the long-term support distros. And the House of Force was originally pointed out 15 years ago. So it's only taken them 15 years to fix that little bug and do a one-line check against how much memory the top chunk should have. So there's all kinds of mess going on with GLIBC, even though compared to other other malloc implementations like Bionic from Android and libstandard for OS X, it's the best protected one. I think Muscle is the least protected, like it's a very simple version. But even with GLIBC being generally like one of the more protected Heap implementations, it's still vulnerable in its latest versions. Yes, sorry.
Any thoughts on UC libc? Same or even worse?
I have no thoughts on UC libc. That's something I need to check out. But
any indication it'd be like Muscle or something?
It would be like Muscle. Okay, yeah. Is it one of like the fast sort of?
Must be. I have not checked either, but I'm now very curious to check.
Yeah, I need to look into that. Yeah, I think lastly, the reason it's easy to think that we see less heap exploitation than we do other memory corruption exploitation like stack exploitation, for example. And I think the reason for that is twofold. For starters today, we've seen that we can corrupt the heap in at least a couple of ways. Overflows, just like the stack, but we also have double freeze and use after freeze, which we didn't cover. So there are more ways to corrupt the heap than there are the stack. And the heap is just as widely used as the stack. And I think so there's no reason for there to be any less heap bugs out there than, say, stack bugs. I think the reason we see less exploitation is twofold. The first is that heap bugs are a little more insidious than stack bugs. So corrupting stack metadata like, say, return pointers or canaries will almost certainly get you a seg fault or an abort. But you can corrupt libc malloc metadata for a free chunk. Unless that chunk gets allocated back by the end of the program, you won't see a crash, you won't see an abort. So unless you're using like the debug heap, for example, heap bugs can be a lot harder to find, even if you're fuzzing, because you might just not allocate a corrupted chunk back. So I think they're just a little harder to find than some of the stack corruption stuff. And also, I just think heap exploitation isn't as well understood in the community. That's why I like to do this stuff. I think we've got a whole conference of people who could probably talk to you about how to leverage stack corruption for exploitation and about ROP, but perhaps a few less people who would be happy to talk about the more involved heap exploitation techniques that go from nothing to a shell with just heap internals like the House of Orange or the House of Corrosion. And there are about 12 other techniques that we haven't covered today. But that's all I got for you guys. Thank you very much for coming. I hope you learned something. Please enjoy the rest of the conference. Thank you.